Boltzmann distribution curves. We use Boltzmann distribution curves a lot in this class. It's a way of really being able to understand the effect of kinetic energy or velocity and the likelihood that something, some reaction, is going to occur. So the generic form of a Boltzmann distribution curve is that on the y-axis you have the number of particles, and on the x-axis you have the kinetic energy. So remember that the average kinetic energy is a measure of the temperature of the system. So here's the average kinetic energy. So the temperature of the system is whatever. So here's one thing that you can see. You can see if I increase the temperature, the rate of evaporation will increase. I know that, right? So on hot days, things will dry out faster than on cold days. How do we understand that with the Boltzmann distribution curve? Well, the purple graph shows the temperature is lower, the average temperature is lower, and this is a cold day, and if this is the minimum Ke required to evaporate, remember that in order to evaporate, you have to overcome intermolecular forces of attraction. And there's a minimum kinetic energy in order to do that. So at the cold temperature, the purple, the number of molecules, which is the area under the curve, that have the minimum Ke required to evaporate is not very high. If I increase the temperature of my system, my curve shifts to the right, I have a higher temperature. More of those molecules, the area under the curve that's to the right of this line, have sufficient energy in order to evaporate. So it helps us understand qualitatively why it is the case that as I increase the temperature, I'm increasing the kinetic energy, certain reactions will occur more easily, right? Because it's all about collisions occurring. Now, we also know that the rate of evaporation depends on the fact that if you have a greater surface area, then evaporation will also occur. And you can think of this as, if this is the minimum required to evaporate, it could be that only a portion of these molecules are at the surface, right? A percentage. If I spread out my molecules, then a greater percentage of these molecules will be at the surface, so I will allow more water molecules to evaporate. So the minimum kinetic energy doesn't change, it's just the proportion of molecules that have that kinetic energy and also are at the surface can change. Okay, so if I take this and say that I have a huge number of water molecules that can evaporate, potentially, but I crumple my towel up so that the surface area is greatly diminished, then basically only a small portion of these molecules can evaporate, and it could be that my towel doesn't dry at all. This is why you need to hang your towel up after you take a shower. Another type of Boltzmann distribution graph has, again, kinetic energy and number of particles, but I'm looking at a reaction from an exo and an endothermic process. So we know that one of the things that happens is that endothermic reactions are harder to happen at certain temperatures than exothermic reactions. Exothermic reactions tend to be more spontaneous. So if I look at a reaction diagram, that's a measure of the energy versus time, and you guys should remember this from biology class. There's a hump. This is my reactants, these are my products, but there's this hump, this barrier that prevents things from just spontaneously occurring, and that's the activation energy. Well, an exothermic reaction, that's my forward reaction, will automatically have a lower activation energy than the reverse reaction. So imagine I'm trying to get a ball from here to here, right? And there's a hump. The hump I have to overcome going from left to right is smaller than if I'm trying to go back up the hill this way. And that's the activation of the energy of the endothermic reaction. So of my reaction, of my system, my activation energy of my endothermic reaction will be higher. It'll be farther to the right on my x-axis than the activation energy of my exothermic reaction. The number of particles that can do something is the area under the curve. So the area under the curve of the exothermic reaction is going to be greater than the area under the curve of my endothermic reaction. More molecules at the same temperature will be able to go through the exothermic reaction than the endothermic reaction. And then the final way that we use Boltzmann distribution curves is to just not look at the kinetic energy, but just the velocity. And look at the gas particles, right? So things that have a higher velocity, I can have a collection, things average velocity here, average velocity right here, and I see that gas green has a higher average velocity than gas purple. And we know from Graham's law that it's proportional to the mass. So gas green has a higher velocity, so it must have a lower mass. Gas purple has a lower velocity, average velocity, so it must have a higher mass. Again, you might have some particles of purple gas that have a higher velocity at that point than the really slow particles of the green gas. We are looking at the peaks. So on average, the average velocity here and the average velocity here.